Okay, just continuing from Friday's lesson on page 18, okay, of the booklet, problem 5. We had to work out the gradient of the curve at this point when x is -1. So the gradient of the curve will be the same as the gradient of the tangent at that point where x is -1. So here, remember, we've got to find another point Q on the curve that's quite close to P. Q would have coordinates x and the y value, so it'd be x and function of x, or x and x cubed minus 3x squared. So there are our coordinates for Q. P has coordinates -1, but we don't know the y value here. So if we substitute sub x equals -1 into our equation, y equals x cubed minus 3x squared, we get -1 cubed minus 3 times -1 squared gives us -1 minus 3, which is -4. So this point here is actually -1, -4. And just doing what we did last lesson, therefore the gradient of the tangent at P will be the limit as x, see Q here has coordinates x cubed minus 3x squared, so as x gets closer and closer, as this x value gets closer and closer to -1, so the gradient of the tangent at P is the limit as x approaches -1, and then we do the gradient of PQ. Now the gradient of PQ, remember, is y2 minus y1 over x2 minus x1. So it will be, now y2 is x cubed minus 3x squared, so it's x cubed minus 3x squared minus y1 is -4, so it's minus -4 over x2 minus x1 is x minus -1. So it's the limit as x approaches -1 of x cubed minus 3x squared plus 4 over x plus 1. So we're going to need to factorize the numerator. Now this is a cubic, so it might be a little bit tricky, so I'm just going to focus this. Okay, but we're hoping that x plus 1 would be a factor. If we just substitute 1 into the x value, we should get 0 up here. Sorry, actually, -1 should be x minus -1 is a factor. In other words, x plus 1 is a factor, which means if you substituted, the root would be -1. If you put -1 in there, it should satisfy that equation. So if we look at that, if you put -1 in here, you get -1 cubed is -1 minus 3, that's -4 plus 4 is 0. So x plus 1 is a factor of that. Now, it does say here, if we can't factorize if we can't do this factorization, we can see what the limit approaches as x approaches -1 by substituting in values close to -1 into the limit. So what we could do, we could substitute the value -1.001 or something like that into that, and then we would see what that limit is approaching. Now, the other thing we can do using our knowledge from 3-unit, I mean, this isn't, you wouldn't do this in a 2-unit paper, but we know that x plus 1 is going to be a factor of that. I can just quickly do a division of x plus 1 into x cubed minus 3x squared plus 4. Remember, that would be plus 0x plus 4. This is not required in 2-unit, of course, okay? And you wouldn't get a question like this in the 2-unit course, but because we can't work out the factorization using 2-unit methods, I'm just going to use 3-unit methods just for some practice here. So x goes into x cubed. Our first thing up here would be x squared. So we go x squared times x is x cubed. X squared times 1 is plus 1x squared. And then we subtract these. We've got minus 3x squared minus x squared is minus 4x squared. And we've got x cubed minus x cubed is 0. And then we bring this down. We've got 0x, which is just going to be 0. And then we bring down the 4. And let's just see what we would get here with this factorization. Sorry, I'll just put the 0 there, 0x. I'll just bring this 4 down as well. actually, I'll just leave this 4 out. I'll just bring down the 0x. So x goes into negative 4x squared would be minus 4x here, would be the next bit up here. So negative 4x times x is negative 4x squared, and negative 4x times positive 1 is negative 4x. So that minus that is 0, and 0 minus negative 4x is plus 4x, and we bring down the plus 4. And x into 4x would be 4 times. So 4 times x is 4x, and 4 times 1 is 4, and we get 0. Sorry, just running out of room there. And so therefore we can see, I'll just focus here. So if we divide x plus 1 into the cubic x cubed minus 3x squared plus 4, we get no remainders, so therefore, and our other factor here is x squared minus 4x plus 4. So this will become the limit as x approaches 1. Now this now has been factorized to x plus 1 bracket x squared minus 4x plus 4 over x plus 1. Now that's 3 unit methods there, which would be the limit as x approaches 1, the x plus 1's cancel. Look, this is a perfect square, which is really x minus 2 squared, but I don't have to put that in now. I can just leave it like this if I want. And then I can, sorry, it's the limit as x approaches negative 1, so I better keep that negative in there. So now we're going to substitute in the negative 1, and we get negative 1 squared minus 4 times negative 1 plus 4, and we get 1 plus 4 plus 4, which is 9. Now, over here in this box, it said if we couldn't factorize if we can't do the factorization, then try to see what the limit approaches as x approaches 1 by substituting in values close to x is negative 1 into the limit. Alternatively, sorry, what I could have done, I could have just substituted, like to check my answer, I could have substituted, let's say, x is negative 1.001 or something like that into this up here. So into x cubed minus 3x squared plus 4 over x plus 1. And when I do that, I'm just going to pause the video and do it. I'll just see what we get. I mean, what we got up here, that the gradient of the tangent at P was 9. When I substituted a point very close to negative 1, such as negative 1.001 into this bit up here, when I put that in, I got 9.006001. So therefore it does seem to be that the gradient of the tangent at P will be 9 at the point when x is negative 1. Now notice the gradient of the tangent at P will at different points on the curve always changes. So up here the gradient of the tangent, if I just move up here, okay, gradient of tangent here is 0. Here I've got a negative gradient. Here I've got a gradient of 0 again. Here I've now got another positive gradient. So the gradient of the tangent to the curve is always changing, which is why at this particular point, when we want the gradient of the tangent when x is negative 1, we do the limit as x approaches negative 1. For other points on the curve, you might do the limit as x approaches 0 if you want the gradient of the tangent here, for example. Okay. Now this is page 19, another problem here. If we want the gradient of the tangent of the curve here, we can see we're going to get a positive value. It's going to be a fairly big gradient. And we need to find a point close to P on the curve. We can just put Q up here, and Q has coordinates x, and the y value would be what this equation is, x to the power of 4 minus 4x cubed plus 16x plus 3 is the y value. And the gradient of the tangent at P is found by doing the gradient. It would be the limit as your x value approaches 3, so as the x value of q gets closer and closer to 3, of y2 minus y1 over x2 minus x1. It's just a gradient formula. So y2 is x4 minus 4x cubed plus 16x. I'll just make some more room, and I'll just focus this as well. Plus 16x plus 3 minus, so that's x2, y2. This is x1, y1, so it'd be minus y1, which is minus 24. So I'm out of screen there. Over x2 minus x1, which would be x minus 3. Now, obviously, if we substitute in x equals 3 here, we're going to end up with 0. We're thinking again that x minus 3 should be a factor of that. I mean, I could substitute in the value of 3 into here and I should get 0, okay? So I'll just tidy this up here. It is the limit as x approaches 3 of x to the power of 4 minus 4x cubed plus 16x minus 21 over x minus 3. Now what I'm going to do instead, we can factorize again so that we're practicing some 3-unit methods, but this is 2-unit content. You wouldn't be required to do that. We could just substitute values of x very close to 3 and like such as 3.001, and then we would get what the limit as x approaches 3 of we would get the answer to this. So I'm just going to go to the calculator and do that now, and you can do the same as well. Substituted x equals 3.001 and ended up into this and got 16.018. So it appears that the limit as x approaches 3 of this function here is 16. Therefore, the gradient of the tangent at P is 16. Okay, now I could always also do this factorization here. Remember, this is not 2-unit, it's 3-unit. So look, we'll just do it for some practice, okay? Plus, remember, we've got no x squared, there's no x squared term here, so I'll go plus 0x squared plus 16x minus 21. Why don't you pause the video and attempt it on your own for some practice, okay? And I'll just work through it now. So we've got x cubed, we've got x to the power of 4 minus 3x cubed. Subtracting those, we've got negative 4x cubed minus negative 3, which is plus 3. It's negative 1x cubed plus 0x squared. X into negative x cubed is negative x squared. So we've got negative x cubed again, plus 3x squared. Subtracting these, we get 0. Subtracting these, we get negative 3x squared. Bringing down the 16x. X into negative 3x squared is negative 3x. Multiplying by that, we get negative 3x squared plus 9x. Subtracting these, we get 7x. Bringing down, sorry, running out of room there. Bringing down the minus 21, we end up with a plus 7 here and get 7x minus 21 and remainder 0. So therefore, just coming from there across here, we've got that the gradient of the tangent at P is limit as x approaches 3, and we can factorize this now, and you'd get x minus 3, x cubed minus x squared minus 3x plus 7 over x minus 3. Now, I don't need to do any more of the factorization here because the x minus 3's cancel. So it's the limit as x approaches 3 of x cubed minus x squared minus 3x plus 7. And now we can substitute x equals 3 in there, and then we get 27 minus 9 plus 7. We should get this answer here of 16 that we got before. And we've got 27 minus 18 is 9 plus 7. And the answer is 16, which is the same as what we got before. So therefore, the gradient of the tangent at P is 16. Now, just to summarize what we've done so far, how do we find the gradient of the curve at P? Well, the gradient of the curve at P will actually be the gradient of the tangent at P. And how do we find the gradient of the tangent at P? Well, we put a point Q, so just coming down here. So how do we find the gradient of the tangent at P? We place a point Q on the curve very close to P. And its coordinates will be x function of x, and the coordinates of P are a function of a. Let's pause the video. So Q is very close to P. We then look at the gradient of the secant PQ. As we were saying, construct the secant PQ, and the gradient of this secant is close to the gradient of the tangent at P. But as Q, this point Q, approaches point P, that means that the x value here will be approaching the x value there. That means as x approaches A, the gradient of the tangent will be the limit as x approaches A of the gradient of the secant. So in other words, the gradient of the tangent at P is the limit as x approaches A of the gradient of the secant, and the gradient of the secant, if this is the point x2, y2, and this is the point x1, y1, the gradient of the secant is y2 minus y1, which is function of x minus function of A, over x2 minus x1, which is x minus a. And we've been using this formula here for the past 6 or 7 examples that we've done. Okay? Talking about limits, I'm actually going to jump to the back of the booklet, which is, if you go back to, you'll see page 50, it appears the numbering stops at page 50, but then turning over, I think we're about 6 or 7 pages from the end. If you turn to the page that says limits, now this would have been page 51 of the booklet, we're going to actually continue from here, okay? Now, moving along the curve towards A, so we notice that as x approaches negative 2, as the value of x approaches negative 2, that y will approach the value of 1. So therefore we can say as x approaches negative 2, the value of y approaches 1. And we can write this in limit notation as follows. We can say limit as x approaches negative 2, y equals 1. So limit as x approaches negative 2, y equals 1 reads as the limit of y as x approaches negative 2 is 1. This means as x gets close to negative 2 but not equal to negative 2, y gets close to 1. It does not actually, I think we're supposed to have a hole here in this curve, not a solid circle. It does not mean that when x equals negative 2, y equals 1. So when we talk about limits, because we were doing limits earlier, and the reason we had to use limits is that when we were doing y2 minus y1 over x2 minus x1, we were getting that the denominator would be 0, and that's why we had to do the limit as x approached a certain value, okay? So the limit notation says we're approaching the point but not getting to the point. So I really should have an open hole here, as in a discontinuity in that curve. Now, an example. As x approaches 0, y approaches 3. In other words, as x approaches 0, y approaches 3. We write that using limit notation as follows. The limit as x approaches 0 of y is y equals 3. So it says, can we write a limit statement of our own by considering this function above? We could probably look at maybe as x approaches, it doesn't matter, as x approaches negative 3, y looks like it approaches 3, or y equals 3. So we could say we can say the limit as x approaches 3 is limit as x approaches negative 3 is y equals 3. Or we could look at another point. The limit as x approaches, say, negative 1 is y equals negative 1. That would be another statement. The limit as x approaches negative 1, y equals negative 1. Okay, they're just some limit statements. Turning over the page, we're going to do some limit statements here. Now this is really what we're talking about, because we've got a discontinuity here at x equals negative 2. So consider this function with a hole in the graph at negative 2, 1. We say moving along the curve towards A, either from either side, we can say as x approaches negative 2, y approaches 1, but it will never equal 1. In other words, we write as x approaches negative 2, y approaches 1. This would be written like this in limit notation. Limit as x approaches negative 2 is y equals 1. So looking here, these two functions, we've got a coloured in circle here and an open circle here. Both of these functions have the same limit statement, because as x gets closer to negative 2, y gets closer to positive 1. So the limit as x approaches negative 2 of y equals 1 means that as x gets closer and closer to negative 2, y gets closer to 1. It does not mean that when x equals negative 2 that y equals 1, okay? Because if we actually found the equation of this graph and factorize, especially like this one with the hole in it, you would find, as what we found before, is that there'll be no value there. There would be no value here at the curve, because the denominator would be 0, okay? When we were looking at the gradient functions before, okay? So the informal definition of a limit is that a limit is the y value a function approaches as x approaches a specific value. Now turning over the page, just this activity here, we can see as x approaches negative 1, let's have a look here, it appears that y approaches positive 4. So writing this in limit notation, it would be the limit as x approaches -1 is y equals 4. You can do the same for these other graphs on this page and then restart once you're finished, okay? Here as x approaches 3, y approaches 4, okay, here. So therefore the limit as x approaches 3 is y equals 4, okay? The next one, now here we've got some discontinuities in the curve and some holes and some sharp points as well. So here we can see the limit as x approaches -2, as x approaches -2, y approaches +4. Writing that in limit notation, the limit as x approaches -2 is y equals 4. And with the last one here, as x approaches -2, we can see here that y approaches -1. Writing that with limit notation, limit as x approaches -2 is y equals -1. Okay, I'm just going to turn over the page. Equivalent limit statements. We know here the limit as x approaches 3 is y equals 4, or we can say, we know that this is the function y equals x plus 1, so we can say the limit as x approaches 3, and replacing the y with x plus 1, so that y is replaced with x plus 1, the answer to all of that will give us 4, because if you substitute 3 in here, the limit as x approaches 3, so once you do the substitution, you drop the limit bit. So you put 3 in there and you get 3 plus 1 is 4. So these two limit statements are equivalent. Okay, so we'll just look down here at activity 2. We're going to complete these two questions now. Okay, with this first one, the limit as x approaches -3. Now, we can see as x approaches -3, y equals -1, but the equivalent limit statement would be to replace the y with actually what the function is. So the limit as x approaches -3 of x squared plus 4x plus 2 is -1, because if you do substitute -3 in there, you get 9 minus 12, which is -3 plus 2 is -1. Okay, also with this one down here, you can attempt it on your own and then restart the video. Okay, the limit as x approaches 5 here appears to be 2, so y equals 2. The equivalent limit statement would be the limit as x approaches 5. Now the function of y actually equals x minus 1 over x minus 3. And so we've replaced the y with what y is here, and then that equals 2. Now if you do substitute in x is 5, let's see what we get. 5 minus 1 is 4, and 5 minus 3 is 2, so 4 over 2 is 2. So yes, that works as well. All right. Now turning over the next page again, if we are given the equation, this is determining limits algebraically. So if we're given the equation of a function instead of the graph, we can find the limit through substitution. For example, find the limit as x approaches 2 of this function x plus 1. So we need to find the value that x plus 1 approaches as the value of x, as the x value approaches 2. So we just substitute x equals 2 into the algebraic expression. And so notice once we do the substitution of x equals 2 in here, we drop the limit as x approaches 2 notation. So substitute x equals 2 into the algebraic expression and drop the limit term at that point. So this means that as x approaches 2, y approaches 3 for this function. Okay, because the answer we got was 3. Turning over the page. Okay, we're just going to, we did some of these last lesson with factorizing anyway, so just a little bit more practice here on limits. So please pause the video and attempt these, and then you can restart it to check your answers. So the limit as x approaches -1 for the function 3x would be 3 times -1. Notice you drop the limit statement once you do the substitution, and your answer is -3. The limit as x approaches 4 for this function is 4 squared, which is 16. For this function, once you do the substitution of 0, you drop the limit term. Okay, so we get 0 plus 0 minus 4, so we get -4. Okay, down here, the limit as x approaches 3. For this function, substituting in the 3, we then drop the limit notation and we get 11 over 4 minus 9, which is 11 over negative 5, or negative 11 fifths. Okay, the next one, we need to do some, with this one actually we don't need to factorize it. I mean, we could factorize it if we wanted, because we do have a difference of 2 squares up here. But if we substitute in x is 2, we don't get 0 on the denominator, so we can actually just do the substitution straight away. The only reason we were factorizing other ones is that if this was the limit as x approaches 1 here, for example, 1 minus 1 is 0, and you can't do that because the denominator of the fraction will be 0, and so that was the reason why we were factorizing before, but in this case you don't need to. So 4 minus 1 is 3 over 2 minus 1 is 1, so the limit as x approaches 2 for this function here is 3. This one over here, the limit as h approaches 0, substitute h is 0. Here, substitute h is 0 and you get 0, and then we get 4 here. So the limit as h approaches 0 for this is 4. Okay? Now, okay, just turning over the page, method 2, factorization and cancelling. The limit as x approaches 1 of this function, x squared minus 1 over x minus 1, when we try the substitution, we end up with 1 squared minus 1, which is 0. Now that is fine up there, but on the denominator we get 1 minus 1 is 0, and it's the 0 on the denominator which causes this statement here to be undefined. So when substitution doesn't work, we need to factorize and cancel to help find the limit. So noticing here that we've got a difference of 2 squares on the numerator, so therefore the limit, so the limit as x approaches 1 for the function x squared minus 1 over x minus 1, we notice this is a difference of 2 squares. It's the limit as x approaches 1 of x minus 1 times x plus 1, and we factorize the numerator there over x minus 1. We can cancel the x minus 1 terms and we get the limit as x approaches 1 for the function x plus 1, which is 1 plus 1, which is 2. So notice we drop the limit term once we do the substitution of x equals 1 in there. So therefore, as x approaches 1, y approaches 2. So in conclusion, if we get a 0 denominator during our substitution into the limit, we need to factorize and cancel to help us find the limit. Okay, you can pause the video now, do activity 2 on your own, find the following limits. The answers are down at the bottom of the page. We've done questions like this before, so you really should have no problems with this. So please just restart the video when you're done. So this is, notice I keep writing limit as x approaches 2 in every step until I do the substitution. Look, if I put x equals 2 in here straight up, I would get 4 minus 4 is 0, so that won't work, so we need to factorize. So keep writing limit as x approaches 2 until the factorization, until we actually do the substitution. Now the factorization is complete, we can cancel from the numerator and the denominator there, and we end up with 1 over x plus 2. Okay, because when these cancel, you get 1's in their place. So now that we're doing the substitution, we substitute x equals 2 in here, and we get 1 over 2 plus 2, which is 1/4. Okay, trying question 2. We keep writing our limit notation until we do the substitution. Notice that the numerator is a difference of 2 squares. So we get x minus 3x plus 3. The x minus 3's cancel, leaving 1's in their place, and we get limit as x approaches 3 of x plus 3. Now that we substitute x is 3 in here, we drop the limit notation, and we get that 3 plus 3 is 6. Now for part 3. Now having a close look at the next one, it's actually the limit as x approaches 2, so I can actually just do the substitution straight away because my denominator will not equal 0. So putting 2 in straight away, I get 2 squared minus 9 over 2 minus 3. Notice I've dropped the limit notation once I've done the substitution, so I get 4 minus 9 over negative 1, which is negative 5 over negative 1, which gives me an answer of 5. So with that one, we did not need to do the factorizing and the cancelling. But with this next one, we do need to do it, because if you substitute in x equals 4 here, you will get 0 in the denominator. So again, keep writing the limit notation until you've done the substitution. Now we've got a quadratic here. We can factorize that. We're hoping that x minus 4 would be one of the factors, and just having a look here by observation, you would get x plus 2, because we've got x squared plus 2x minus 4x minus 8, and that works. The x minus 4's cancel, leaving 1's in their place. So it's the limit as x approaches 4 for the function x plus 2. Once we do the substitution of 4, x is 4, we drop the limit notation and we get that our answer is 6. Okay? Now, just turning over, there'll be a blank page, and then following that page, there's another page. Sometimes you don't want to factorize things like this. For 2 unit, that would be too hard. In 3 unit, you could do this by division, divide x minus 3 into this polynomial up here. But if you were in 2 unit, you could actually just substitute values of x that are very close to 3 in here. If you put x equals 3 in here, the denominator is 0, which is undefined. So that will not work. So what we do is we don't want to factorize the numerator, so you can do what we were doing before, which is substituting some values of x very close to 3. Here they've tried 3.01 and got 16.18. Trying 3.001, you get 16.018. Trying 3.001, we get 16.008. We feel quite confident and sure that the value that's being approached is 16, and thus we can write the limit as x approaches 3 for this function is 16, meaning that as x approaches 3, y approaches 16 for this particular function here. Okay? Sorry, for the next question here, activity 3, just trying this question here. Determine the limit as x approaches 1 for this function by just using substitution. For example, you could substitute something like x equals 1.001, which is very close to x equals 1. You can pause the video and attempt this yourself. Now, substituting x equals 1.001 into this function, I get negative 2.999, which looks like it's approaching negative 3. And so therefore the limit as x approaches 1 for this function, x cubed minus 3x squared plus 2 over x minus 1, is negative 3. Again, another way of doing this, but using 3-unit methods, would be to factorize or divide x minus 1 into x cubed minus 3x squared plus 2, and hence factorize that quadratic. But notice there are no x terms, so I'd go 0x plus 2. This is not required for 2-unit, but it's good, some good practice here for 3-unit polynomials. So just factorizing this, just try it on, pause the video, try it on your own, and then turn it back on once you're done. And I'll just do it here as well. Negative 3 plus minus negative 1x squared is negative 3 plus 1x squared, which is negative 2x squared. Bringing the 0x down, don't forget to put 0x here, otherwise you're going to make a mistake there. X into negative 2x squared is negative 2x. Multiplying through by the negative 2x, you get negative 2x squared plus 2x. Subtracting, we get negative 2x. Bringing this 2 down, and then x goes into negative 2x. The factor would be negative 2 up here. So we get negative 2x plus 2. We get 0 remainder. And so therefore, we can now have a look at our question, which was, and I'll just write it down here again, the limit as x approaches 1 for this function, x cubed minus 3x squared plus 2 over x minus 1, is the same as doing, just get rid of that, the limit as x approaches 1. Now, this is the result of our division here of x minus 1, x squared minus 2x minus 2 over x minus 1. Cancelling the x minus 1's in the numerator and the denominator, we get the limit as x approaches 1 for the function x squared minus 2x minus 2. And so when we substitute 1 in there, we get 1 squared minus 2 times 1 minus 2 is 1 minus 2 minus 2, which is negative 3. So our answer is negative 3, which we did and got up here. Okay, so substituting something like this would be the best way to go. Remember, it is 2-unit and not 3-unit here. Okay, So this answer where it says -2 up here seems to be incorrect. The answer is actually -3. Okay. Now just looking at the very last page of this booklet, tips for writing and setting out limits. The limit part should be written in bigger writing than the x approaches a part. So notice here, limit is written quite large, and this is written smaller, x approaches 1, and your function here is normal size, x plus 2. Okay, setting out limits, you only drop off the limit bit after the substitution. So notice limit as x approaches 2 of this function, we've factorized it, we've still got limit as x approaches 2 there, cancel the x minus 2's here, so we've still got limit as x approaches 2 for this function, but once we substitute in the x equals 2 here, we then drop the limit notation. So this is done correctly, whereas this over here is incorrect, because the limit as x approaches 2 has been dropped off before the substitution is made. So there should have been limit here and limit written there as well. So it was missing limit as x approaches 2 for those two lines. And also the equal sign must be to the far left of the limit or the far right, but never in between, okay? So limit as x approaches 3 here is equal to all of this. Limit as x approaches 3, they've factorized, now they've cancelled here, okay? And now once they do the substitution, they drop the limit. But over here, for example, this is written incorrectly. Notice the limit as x approaches 3, and then they put the equal sign there. So that is incorrect. You do not put the equal sign there. It needs to go to the front here, okay? So making sure that the equal sign is at the beginning, okay? Now if you don't do that, you could lose marks. Also, if you drop your limits sign before you do your substitution as well, you could also lose marks. So you need to be really careful using this notation. You could please go to chapter 8 of the textbook, exercise 8.3. You'll see that there is a section on limits, okay, and it's just what we've been doing, where you're just working out some limits for some different functions. If you could please do, wait a sec, I'll just get that back to the right page. So please just do exercise 8.3. You can do question 1, let's say every second question, like 1A, C, E, G, and I. Actually, I'd like you to try J as well. And you could also do question 2, just do every second one in that as well. Question 2A, 2C. Now you're going to have to factorize out the H in the numerator here. With this one, again, because you can't substitute H in the denominator, you need to take out a H from the numerator there. So just try A and C. Look, a lot of these look very similar, where you're just taking H out. Here you'd need to take out this delta X out, okay? So try A, C, E, and then you can try G and I. Okay, so you're just pulling out a delta X there from each of these terms. Now this here is delta X squared, so if you pulled out one delta X, you'd still have another remaining delta X there. Okay, so just doing exercise 8.3 for homework.